Okay, guys, today we're going to talk about momentum and we'll also talk about transfers of momentum and how the law of conservation of momentum will tell you how much can transfer. So we're going to start with what does momentum involve. So a good definition of what momentum is would be a measure of how hard it is to stop an object. So when we think about something traveling and moving, how hard it is to stop an object will really depend on two different things. One would be how big the object is. If a baby stroller was rolling down the street, you could probably step in front of it, stop it, be a hero pretty easily. But if a train is going down the tracks, you cannot stop that easily at all. It's not going to end up very well for you. So mass is definitely one of those big factors.
Fly versus windshield. Part 1. The RV. A fly has momentum. So does an RV.
I'm devastated that you're getting married. I'm just devastated. I thought I was the one.
Yeah, well, me. Huh? The RV's momentum wins. Don't even bother tuning in next week to Fly versus windshield.
The other is how fast that object is traveling. So it is a factor and it can make small objects still have a lot of momentum. Because even if you're lacking mass, if you have a ton of velocity, it could still be very hard to stop the object. So we got an equation that we can calculate what momentum is. This one's pretty easy to deal with. We're just going to multiply mass and velocity together. The symbol that we use for our labels, a couple of them are very familiar. We have kilograms here. We should be familiar with that. Mass, meters per second for velocity. And we're not going to worry about a direction, so we can treat velocity the same as speed. But momentum, we got kilograms times meters per second. It's not squared like we did with newtons. This is just mass times a velocity. To get newtons, you had to do mass times acceleration. So it is different. And it doesn't tell us a lot of information other than we factored mass and velocity together, and this is the number we got. Bigger numbers will win in collisions. So symbolically, with momentum, little p is the symbol for momentum. M's taken for a lot of things, so they went with a Latin root of the word to get the symbol. Then we go M is mass, V velocity. So the label, again, kilograms, meters per second, tells us that it depends on both factors, mass and velocity. So if one of those is zero, so zero mass would be not very likely, but if velocity was zero, we plug in zero right here, that means momentum automatically is zero, because momentum is how hard it is to stop the object. If the object is already stopped, we don't really have a measure of that. So something small can still have a large value of momentum based on that velocity. So even if this number is really small, or mass, if the velocity number is really, really huge, it could still make this number really significant. So if you are a fan of those circle charts we use, you could still use those circle charts for this. Remember, this is momentum. We have mass and velocity. So if we wanted to figure out mass, for example, momentum divided by velocity. We want velocity, momentum divided by mass. And if we want momentum, as we saw on the last slide, mass times velocity. So here's an example for us. What is the momentum of a ball that has a mass of 10 kilograms and is rolling 10 meters per second? This is about as straightforward as momentum problems can get. We don't have any angles in high school, angles will become involved, and so velocity will be important. For us, speed could be substituted for that. So we know our equation. Momentum is mass times velocity. So we see kilograms right here, and we know that's our mass. We see meters per second here. We know that's our speed, so that's our velocity in this case. So all we're going to do is multiply those together. So number-wise, it should not be real challenging. 10 times 10, we should get 100. But notice on our label, nothing canceled here. Kilograms, meters, and seconds, nothing's there to make it cancel out. So we got to keep every single thing kilograms times meters per second. So again, we factored mass and velocity together, and we got 100. It doesn't give us details that was mass small and velocity big, was velocity small, mass was big. It just says the result factor. So during a collision, transferring momentum could happen. So one object might lose momentum, the other object would gain that momentum. And we will be seeing this in our lab. But sometimes they can bounce opposite directions, and that's an elastic collision. But the total momentum in the system should still be the same. So a football player tackling another football player, one person might lose some of their velocity, some of their speed as they approach, but that other person might lose their speed going the other direction and maybe even get pushed another direction. So momentum is transferred from player to player. So if you're a small football player, that doesn't necessarily mean you can't tackle anybody. What you lack in size, you just have to make up with your velocity. If you like the game of pool, on the break during billiards, what it's formerly called, the cue ball, the white ball, hits all the others. It loses momentum, but that momentum is transferred throughout all the others, and they go all over the table. So we will see this transfer as a law and work through a scenario to show you how totals stay the same.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So, for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So, for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So, for example, if I can get these two to stick together, while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle since the total momentum of the system has to remain constant.
So with this law of conservation of momentum, this is a big concept for us. The law states the total momentum before a collision is equal to that total momentum after the collision. So notice we highlighted total here. because that is the key term. That's not saying that both momentums have to stay the same for each object, but if one loses momentum, the other one has to gain that same momentum. So the total has to be the same. So one object can lose, but the momentum must be accounted for somewhere. If an object gains momentum, something else had to lose it in order for an object to gain it. The total has to stay the same. So this little video clip will show us, let me change my pointer. How this total is staying the same. So if one mass comes in, the collision, one mass has to go out because it lost its velocity, so it has to have the same come out. So now he'll do 3 masses in, 3 masses out, just because of the law of conservation of momentum. Now it does slow down and stop, and that's a question some people have, is why does it slow down and stop? Well, there's a lot of friction and air resistance that add up over time to make that eventually stop. So if there was no friction, no air resistance, and he did that, he would be doing that forever. So the system would start and it'd be in perpetual motion, meaning it won't stop. So here's our in-depth example about that law of conservation of momentum. And we want to figure out the velocity of ball B. So before the collision happens, let's say this is ball A, this is ball B. So ball A is traveling 4 meters per second, and it's 2 kilograms. Ball B is also 2 kilograms, so it's at rest. So this ball is going to come in and hit the other. After the collision happens, this is ball A. It comes to a complete stop. We want to know how fast ball B is going. So we could just reason through this very easily because they're the same mass, and we could probably guess what our end velocity is going to be. But that doesn't happen all the time, because if these masses were different from each other, you couldn't just use the speeds to get your answer. So if you see what I'm talking about right now, you might have an answer in your head. But we're going to show you how to reason through it with the conservation of momentum law. So before the collision, we need to know the total momentum before this collision happens. So that means we need to get the momentum from ball A, and we need to get the momentum from ball B. And there is a big fancy equation for this, but we're going to kind of piece it together because I don't know where you guys are in math about solving equations. So before the collision happens, ball A's momentum, mass times velocity, should be 8. Ball B, mass times velocity, which is 0 in this case. Sorry about that 0, that's really bad. Should be 0. So our total momentum before this collision happens, 8 plus 0 equals 8. So if we think about that law of conservation of momentum, we know that the total momentum before the collision, which is 8, has to be equal to the total after the collision. So what we can do is assume right here, the total's 8, so after, the total is going to be 8. So we just need to know how much of that 8 came from ball A and how much of that 8 came from ball B. So the momentum of ball A, we can figure that out right now because we have mass, we have velocity, which is 0. That's a better 0. Good job. So we go mass times velocity, we get 0 momentum. That means 0 of the 8 came from ball B. So we can just kind of assume now that, hey, the total is 8. 0 of that came from ball A. That means 8, all of it basically, came from ball B. So we have the momentum, which is 8. We have the mass, which is 2. We can figure out the velocity of ball B. So if we bring up our circle chart, we're going to figure this out. Remember, our momentum was 8. Our mass was 2. So we're going to use that equation to figure out what we're going to do to get velocity. So we're going to cover up velocity because that's what we want to know. So that shows us that we're going to get momentum divided by mass. So if we do this, we see that kilograms is on top and bottom. It's going to cancel out. 8 divided by 2 gives us a 4. So the only thing we're left with here, meters per second. So we tag on meters per second. In high school, it will be important to have a direction because you're going to deal with angles. But for us, 4 meters per second is fine because we're dealing with one-dimensional motion. So that would be a problem you work out. And if you knew 4 meters per second before we even started that explanation, that's good. You kind of see the pattern. But don't always assume it works out that way, because if those masses were different from each other, it wouldn't be like that. We would have different types of velocities. So if we had like an extra credit problem or anything like that, you have to work through it how we just worked through this one in order to get the right velocity. So remember, you can always pause, you can always go back, make sure you have watched, make sure it's in your notebook, and we will get going with the next thing.